Did you know you are a walking periodic table? Seriously, it sounds kind of crazy, but it's absolutely true. Just take a second and actually look at your hands. Maybe feel your pulse. Your body is quite literally 96% made up of just 4 core elements: carbon, hydrogen, oxygen, and nitrogen. I mean, that carbon, it's the literal scaffold holding your very cells together. And the iron in your system is physically pumping red through your veins right this second. You are walking, talking, breathing chemistry. And, these elements don't just make up us. They're the whole story of our daily lives. Just think about a normal morning routine for a second. You wake up, take a deep breath of oxygen and nitrogen, you reach over to silence your phone, a gadget that's completely reliant on a lithium battery and silicon microchips, by the way. Then you head to the bathroom to brush your teeth with fluorine-infused toothpaste and wash your hair with zinc-fortified shampoo. So chemistry isn't just something happening in a lab somewhere. It is the invisible, ever-present engine powering literally everything you touch, taste, and use. So, welcome to today's explainer, decoding the periodic table, the map of life. Now, I know for a lot of us, the periodic table kind of brings back some high school trauma. We usually remember it as this super boring, overly complicated grid of boxes we were just forced to memorize. But today, we're going to completely reframe that. You don't have to memorize a single thing, I promise. Instead, we're going to explore this table for what it truly is, a beautifully dynamic, living map of the universe's most fundamental building blocks. All right, let's dive right into this. Here is the roadmap for our journey today. We've just touched on the map of everywhere. Next, we're going to cover Mendeleev's brilliant puzzle, decoding the elements, touring the neighborhoods, calculating the core, and finish up with a living, evolving chart. Let's get to it. So let's jump right into Section 1, Mendeleev's brilliant puzzle and the history of organizing elements. To really appreciate this map, we kind of have to look back at how chaotic things used to be. Early chemists were essentially stumbling around in the dark. In 1789, Antoine Lavoisier took the very first step by grouping simple substances into really basic categories like gases and metals. Fast forward a bit to 1864, and John Newlands noticed that every 8th element shared traits. He called it the law of octaves, kind of comparing them to musical notes. Fun fact, his peers actually laughed him out of the room for comparing science to music. But then, just 5 years later, in 1869, a Russian chemist named Dmitry Mendeleev stepped up and proved that a brilliant underlying rhythm actually did exist. But here's the thing. What made Mendeleev a true, undisputed genius wasn't just how he organized the known elements, it was what he chose to leave out. Mendeleev intentionally left gaping holes in his table. He treated the whole thing like a giant puzzle, boldly predicting the existence and exact properties of undiscovered elements. Like, he predicted an element he simply called Eka aluminum. Years later, scientists actually discovered gallium, and its weight, density, and melting point matched Mendeleev's predictions almost down to the exact decimal point. Talk about a total mic drop moment for modern science. Moving right along to Section 2, decoding the elements and how to actually read this map. If the periodic table is basically a sprawling city map, the rows and columns are its exact grid coordinates. So let's start with the horizontal rows. These are called periods, and there are 7 of them in total. A really easy way to visualize this, think of atomic electron shells like seats in a stadium spreading out from the field, where the field is the nucleus. Every single element in a specific row has the exact same number of seating tiers. And as you move from left to right across that row, each element simply adds 1 more proton to its nucleus than the guy sitting right next to it. Next up, we have the 18 vertical columns, and these are known as groups. Elements living in the same group are essentially chemical siblings because they share the exact same number of valence electrons. Think of valence electrons as the hands of an atom. They're the outer parts that literally reach out to grab onto other atoms to form relationships and bond. Because elements in a single group have the exact same number of hands, they react and behave in remarkably similar ways. Now think about the massive amount of data packed into just a single element box. You got your standard 1 or 2 letter symbol, like Fe for iron, usually sitting right above its full name. Down at the bottom, there's the atomic weight, which represents the average mass of both protons and neutrons. But shift your mind up to the top for a second. See the atomic number? That is simply the number of protons in the atom. It is the absolute, unchanging ID tag of an element. It gives us an instant, perfect indication of exactly what that element is and how it's going to behave. Which brings us to Section 3, touring the neighborhoods, or the chemical families. Stepping back to look at our sprawling city map, we can start to see these really distinct, highly unique neighborhoods. The biggest divide by far is between metals and nonmetals. Over on the left, in the center, the solid, shiny, heavy metals absolutely dominate the landscape, and they're fantastic conductors of heat and electricity. Then, way over on the right, you have the nonmetals. These are often gases, but when they are solid, they're dull, brittle, and frankly, terrible conductors. But right down the middle, acting like a crucial border wall, are the metalloids. Elements here, like silicon, actually possess traits of both sides, making them perfect semiconductors. Let that sink in for a second. That totally unique middle ground property of silicon is literally the entire reason the modern computer age even exists today. And these neighborhoods, they are home to some mind-blowing extremes. Take the alkali metals in group 1, like sodium. These guys are violently reactive. They'll literally explode if they even touch water. Now, jump clear across town to group 17, the halogens, like chlorine. This is a highly toxic, lethal green gas. But, and here is the absolute ultimate punchline of chemistry. When you take that explosive sodium metal and you combine it with that highly toxic chlorine gas, they perfectly neutralize each other's extremes to form ordinary, edible, totally safe table salt, NaCl. It's just this stunning display of harmony. Meanwhile, right next door in group 18, the noble gases like neon are completely chill and stable, just refusing to react with anyone. Next up is section 4, calculating the core and finding those hidden neutrons. Okay, so we've talked a whole lot about protons and those electron hands, right? But what about the neutrons hiding deep down inside the nucleus? Well, the map actually reveals that secret really easily too. So how do we find them? It just takes 3 super simple steps. Let's use carbon as an example. Step 1, you find the atomic weight at the very bottom. For carbon, it's 12.011. Step 2, just round that to the nearest whole number to get your mass number. So 12. Step 3, subtract the atomic number, which is the number of protons at the top. Since carbon is element number 6, you just do 12 minus 6, which equals 6. And boom, just like that, you've calculated the exact number of neutrons inside an atom's core. And finally, section 5, a living, evolving chart and the future of the periodic table. So it's really important to remember that this map isn't some dusty, dead historical artifact. It's an active, constantly evolving tool managed by the International Union of Pure and Applied Chemistry. Actually, back in the early 20th century, new physics almost broke Mendeleev's masterpiece entirely. Scientists discovered isotopes. These are basically atoms that have extra, super heavy neutrons, which totally throws their weight off. And because the original table was organized by atomic weight, everything suddenly just fell apart. The whole pattern was ruined. But one scientist realized that the unchanging proton count, the atomic number, was the true organizing rule. The table snapped perfectly back together. Today, the map contains exactly 118 officially recognized elements. With recent additions over the last few years, like tennessine, scientists have completely filled out that 7th row at the very bottom. But honestly, here's the coolest part of all this. These super heavy, brand new elements, they aren't dug out of the ground somewhere. They are entirely synthetic. They're smashed together in massive particle colliders, and they literally only exist for a tiny fraction of a millisecond before decaying. I mean, it is pure, real-world sci-fi happening right now. And the rules of periodicity clearly suggest that an 8th row is just waiting to be started. Which leaves us with an incredibly thrilling, provocative thought. What undiscovered elements might be waiting just off the edge of the map? What impossible properties might they hold? We started out today by looking at our own hands, right? At the ancient carbon and iron holding us together. Now, we're looking forward to the absolute cutting edge of the future. So keep your eyes on the chart, because the map of life is still being drawn.